Namaste. All right, hey guys, here's what I wanted to do for you guys. Since we started the concept of work, and hopefully you watched the video on work, I want to do just a couple of quick example problems for you. So it shouldn't take too long, so that to relieve like any anxiety or whatever that might happen as you're doing the problems. Okay, so let me give you one right here. So let's say that we have a car. All right, let me get out my official piece of paper. All right, so let's say that we have a car, and the car goes and it has mass, so 1,000 kilograms. Okay, good, you guys can see that. And all right, so the car starts from rest and it accelerates, okay? And it accelerates through a distance of through a distance of 60 meters, okay? And at the end of that time, at the end of that distance, it's going 20 meters per second. And what I want the average force provided by the engine in accelerating it from 0 to 20 over a distance of 60 meters, okay? And one of the ways we could do that is with the concept of work, because remember, work is a change in energy, all right? And it's also related to a force, because a force causes an energy change. So forces acting over a distance cause an object's energy to change, either give it energy or take energy away. So it's also equal to force acting over a distance, all right? So we have that. All right, now if we look at the car, what type of energy has been changed? Well, it started out not moving, and then at the end of the situation, it's moving, so gain kinetic energy. So we can say that the energy change, or the work done, is a change in kinetic energy of the car, okay? Well, so that would actually be K minus K naught, all right? But K naught is 0 because it's not moving, okay? So I can shorten this up a bit, and I can say that the energy change is equal to 1/2 mv squared, where v is that velocity there that it has at the end of the situation. And so what I could do then is I can say, because this is the work done on the vehicle, so I can say that 1/2 mv squared is equal to force, the other equation for work, which is force times distance. And in that case, then, if I'm looking for the force, I just divide by the distance on both sides. All right, and that's going to take it away over here. Okay, and then when I did this and I plugged in my numbers, so you're getting 1/2, 1,000, and then 20, and be careful because you have to square it. All right, and we're going to divide that by 60. When I did that out, I got that this calculation wound up being 3,000. It was all threes for whatever, or 3 repeating, newtons of force, okay? Or about a ton of force, something like that is about, actually under a ton. But anyway, so that's how I figured that out, okay? Now, I wanted to do another type of problem for you, or another problem for you, okay? And again, I'm going fast, but I know that you guys can slow this down as you need to. So let's do something like this. This is a little bit more advanced. So let's say I have a mass over here, okay? And I have a 30-degree angle that it's on an incline, okay? And so let's say that we're going to accelerate now over a distance of 200 meters up a hill, okay? And so up here, the mass is now traveling, has a speed of 15 meters per second, okay? Okay, so what is the average force causing the object to accelerate to that speed up this hill over that distance, right? Well, again, back to remember this is all one equation, just has various forms, and you have to pick the form that fits the situation. Work is a change in energy, okay? Well, what kind of energy is being changed here? Well, it's at the bottom of the hill, it doesn't have potential or kinetic. At the top of the hill, it has both potential and kinetic. So the energy being changed is, I have a change in potential, plus I have a change in, I'll fit that in there, plus I have a change in kinetic. All right, so that being the case, the work done, which is also a force times the distance, is equal to the potential energy that it gained, mgh. Now really that's a change, but if you're starting from 0, so it's mgh minus mgh naught. But if you're starting from 0, all right, u naught is 0, k naught is also 0. So plus 1/2 mv squared. Okay, and then, okay, all right, just be careful. I got that, the h there, be careful, because the h is not right here is not 200 meters. The h is the height that it rose above the 0 point, and the 0 point is the ground. So I know I'm cut off with the equations here, but this is going to be 200, which is this length here, times the sine of 30 degrees, which winds up being 100 meters. So it goes up a vertical distance above the ground of 100 meters. Okay, so when I solve, in this case, all right, when plugging it in, I get that the work is equal to mgh, so that's 1,000, 9.8, 100 plus 1/2, 1,000, and then 15, and be careful, you have to square it. All right, when I did this out, I got that this is 980,000 joules. And when I did this part all out, I got that this was 112,500 joules. Okay, and when you put the two together, it's, all right, the work done is 1,000,000. All right, 92,000 and change joules. Okay, and of course this is equal, if I'm looking for the average force provided in causing this object to accelerate up the hill and reach that speed, then this is equal to the other work equation, which is a force times a distance. Now be careful, because in this distance, that distance, that is the distance that the force is working. All right, it's not the distance above the 0 point. That's for potential energy. Okay, so dividing by d, the force is divided by the distance, which is 200. So if I divide by d on both sides, okay, and then when I do that out, all right, and give myself a little more board space there. Okay, when I do that out and divide this by this, I got that the force caused to accelerate that object up the hill and reach that speed winds up being about 5,000 and change. Okay, all right. Again, I just wanted to do some various examples for you so you could see how I'm using both the energy version of the work equation and the force version, F times D, force version, there we go, of the work equation, how you can put them together, set them equal to each other to fit the situation, depending on what you're being asked, all right? Okay, so, all right. If you guys have questions, make sure you guys are seeing me during my office hours from 10 to 11, and I'll be around, okay? Go out and enjoy your apocalypse.